to tee up the introduction. I know that Jessica's going to go through.
Of this year, our Mount Tam members only star parties are canceled, postponed. We will switch all of the members only parties to virtual parties. And then also the lectures on Mount Tam have also all gone online for this year. We are encouraging more virtual parties this year. So if you have what is this scope?
TV.
That scope.
TV.
And you would like to participate, let us know, and that'd be great. The next one is on September 26th. We, as a board, are also coming up with protocol that will be used with all of our in-person star parties when we are allowed to have them again. And then the next quick mention is we have started thinking about our elections for the 2021 board. So if you are interested or want to know more information, please email myself or PJ or any of the board members. We are looking for some more board members, and that commitment is we have one meeting a month, 8 of which are online and 4 in person, but they're now all online, and then any other project that you want to take. So it's as much or as little work as you'd like. And this year we have also switched to electronic ballots. But if you would like a paper ballot, you can just request one and we will send one to you. And voting will not take place until, I think it's November. So thank you, Liz. But we just want, if you're interested in that, please email us. We would love to have you, and we just want people to start thinking about that.
Hey, Jessica, if you don't mind, I'd love to just add too, there are no special skills requested of board members. Everybody's got something to offer, and you don't need to be an almost professional grade astronomer to be a member of the board. You just need to have a little extra time and the energy and the willingness to do this. It's very rewarding. It's a great way to meet some of the people in our club who obviously share this interest. So if you think you're not qualified, don't think that. You probably are, and we'd love to have you.
That's it.
Are you finished, Jessica?
Yes, I am.
Oh, very good. Erin, I'm Linda Mahan. I've been emailing you, and thank you so much for joining us tonight. I'm going to first introduce the next 2 month speakers. On October 21st, we need to start our lecture a half hour early because our speaker is from Hershey, Pennsylvania. And it's 3 hours later for him there. It's Bob Noya, Robert Noya, former SFAA member. He used to be the editor-in-chief for Mercury magazine at the Astronomical Society of the Pacific. He's an award-winning science writer. He was the editor-in-chief for Sky and Telescope magazine for several years until he retired. His topic is finding life on other worlds. Are we alone, or do we share our solar system and galaxy with other life forms? Right now, we don't have the answers to these profound questions, but scientists are in hot pursuit. The technology of searching for life on other worlds has received a level of maturity where the first definitive evidence could come in the very near future. So that he would like to begin speaking at 7:30 next month, October 21st. On November 18th, always we meet on the third Wednesday, 12 years of cosmic fireworks with a Fermi Gamma Ray Space Telescope. The speaker is Eric Charles from SLAC National Accelerator Laboratory. A single gamma ray carries millions of times the energy of a single photon of visible light. Gamma rays are produced only in the most convulsive environments in the universe. The Fermi telescope was launched in 2008 to measure these extreme events, and it has changed our understanding of the most violent objects in the universe. Tonight's speaker, Aaron T. Lee, is a professor of physics and astronomy at St. Mary's College of California. Is that in Moraga?
It is, yes.
In Moraga. He was a postdoctoral scholar at the University of Texas in Austin, where he worked with Stella Offner. He was a graduate student and National Science Foundation graduate fellow at UC Berkeley and worked with Chris McKee and Steve Stahler, both of whom have spoken to SFAA in the past. Prior to graduate school, he completed part 3 of the Mathematics Tripos at Cambridge University and was an undergraduate at Northwestern University. Aaron views astronomy as a gateway science and is excited for the opportunities to use astronomy as a means of introducing people to the wonders of science and the scientific method. Tonight's talk, the formation and evolution of binary stars. You'll be speaking to a group of people with telescopes, some of us who love double stars. I'm so pleased, binary stars rather. Happy that you'll be speaking to us on this topic. Nearly 50% of the stars we see are parts of a binary system. Double stars and multiplicity of stars are a common phenomena in the Milky Way. Our speaker will discuss the process and how observations using some very powerful supercomputers we'll discuss the process and how observations and start of stars and galaxies and how they rely on our understanding of stellar binarity. I'm so pleased that Aaron Lee is going to speak to us now. Thank you so much.
All right, thank you so much. I've become an expert at navigating Zoom rooms as now all my classes are on Zoom.
Yes.
I think it would be easiest if everyone does a double check to make sure that their mics are muted so that we don't get weird feedback of your speakers. And so let me go ahead and share a screen. Let's see. All right, so hopefully you should see just a title slide and not all of my notes. Yes. Of course, I just asked you to mute and now I can't see anyone's face. So someone has to unmute and confirm.
Yes, we just see the title slide, no notes.
Okay, very good. You can't see my cheat sheets. All right, very good. Thank you so much for having me here, wherever here is for you these days. I look forward to future times when we can hopefully convene together and gaze ever skyward towards the celestial wonders, whether it be double stars or other objects in the universe. Tonight, I'm really excited that I can share with you some of my more recent work that I've been doing over the past couple of years, which, as was mentioned, I started doing this work primarily at the University of Texas in Austin, where I was a postdoc, and now I'm continuing to work on it here now as a professor at St. Mary's College of California in Morocco. And most of this work, again, being done at first at the University of Texas in Austin and continuing here, it really would not have been possible without my collaborators, a bunch of incredibly talented and smart women that I must acknowledge in everything that I do. So this actually is a reunion of sorts. I have not had a chance to talk to you since 2015, where I was just a little grad student, kind of looking at myself right now on the screen. A little green, a little younger, a little thinner. Yeah, 2015 I gave this. This was right when I was wrapping up grad school. So I apologize for my prolonged absence, but I would like to believe that maybe it was SFAA that drew me back to the Bay Area. And just to give you a little recap, this was kind of already recapped already. Like what have I been doing since 2014 when you last heard me give that talk? Not that you asked, but here we go. So I graduated from UC Berkeley, and kind of the next leg of your academic journey is to do a postdoc, which I kind of explain as a professor in training role. I know you've had a couple of you recently had the Miller Fellow postdoc from UC Berkeley talk a couple meetings ago, which is awesome. I had the absolute pleasure of being able to get a position with Stella Offner, also a UC Berkeley alum. We actually have the same PhD advisor, Chris McKee, who at the time was a professor at the University of Massachusetts, Amherst. So after spending, too many years, 7+ years here in grad school, me and my partner in crime packed up our car and began our cross-country journey, where I began the next part of my academic journey as a postdoc with Stella. Less than a month after arriving at UMass Amherst, she informed us that she had gotten a new position, a better position, at the University of Texas in Austin. So after about 8 months in Massachusetts, we packed up our life again and then traversed back to the South, where I completed the remaining 2 years of my postdoc in the University of Texas in Austin. From there, the next kind of leg of your journey is to become a professor. So I, did the whole job market search last fall. Thankfully, ended up getting 2 positions, one here in the Bay, St. Mary's, and one, let's just say, not in the Bay. So the choice was pretty clear that what I had to do was pack up my life again and return back to the Bay Area. My cat Geo is ecstatic that this is the first year in quite a while where it seems like we haven't been relocating after staying in some place for 12 or 24 months. And I hope to hopefully be staying here for a good long while. But it really is us coming full circle. One of the first things we teach in our physics classes here at St. Mary's is the idea of displacement or net change. How, over a certain amount of time, how much have you relocated, in a net amount? So I started at Berkeley, I ended up in Moraga. So if we were to do this systematically, I would say that over the last 4 years, I've more or less traveled 10 miles, 10 miles to the east. So what to take of that, I'm not sure, but overall, I'm pretty happy to be back. All right, the actual talk. We live in a universe that is filled with stars. Since prehistoric times, humans have gazed up in wonder at their nature and origin. And of course, this is a worthwhile endeavor because we live around such a star, the sun. It is the source of all of our energy and existence. On a clear night, one free from haze and smog and falling ash, you can see roughly a few thousand stars as long as you don't have too terrible light pollution. But we now know that there are over 300 billion stars in just our Milky Way Galaxy. The Milky Way Galaxy being one of likely trillions of galaxies and just the part of the universe that we know of. A universe that we now know of to be nearly 14 billion years old. We now know that these galaxies are primarily composed not of regular matter like what we're made up of, but of this elusive dark matter, which emits no radiation. We know that this universe that we live in is not only expanding, getting larger with time, but is expanding at a faster and faster pace. And we know all of this, or at least have begun to learn about much of this, because of stars and the light they emit. So stars pervade. They tell us a lot. Their light is what allows observational astronomers to look into the universe and learn about its contents and its evolution. So it's worth knowing about stars themselves. What are these things we call stars? And we now know that not all stars are created equal. Some are quite large and some are quite red. Some are different colors like yellow or white or blue. Some are giants, some we call giants, some we call dwarfs. Some stars end their lives as a grand celestial firework that explode, and individual stars may outshine entire galaxies for days. While some stars just more gradually and simply fade away. If a supernova, which is what was in the upper right, is a cosmic firework, stars that do not quite explode but just kind of drift away like the planetary nebula you see, I might call a cosmic burp. Some of these stars become black holes, some become neutron stars, some white dwarfs. Some stars are just barely able to maintain nuclear fusion in their cores. So there's a complexity to stars. Stars themselves, there are intricacies that are worth knowing about how stars behave and work. And we now know that they aren't actually snowflakes. Not every star is completely unique because we have physics to understand how stars work, are made, and evolve. And from this, we have come to learn through images like the one you're seeing, which is an image of the sun. If you take sunlight and put it through a very expensive and fancy prism, that by looking at the kind of light that stars emit, we now know that stars are not made up of some exotic matter, but are made up of the same elements that make up our periodic table. In fact, we now know that the periodic table comes primarily from stars. Stars die and eject elements back into the universe that eventually populate to create the periodic table we know today. So when Carl Sagan says we are made of star stuff, it is wholeheartedly true because the stars and their byproduct are the primary origin of all the elements that make up the universe, except maybe perhaps hydrogen and helium, which were created during the Big Bang. We are here because of stars. We know the universe because of stars. So that's what, just that alone gets me interested in stars. That alone gets me really fascinated to know kind of how stars behave and work. And that question has been more or less solved and figured out over the last 2 centuries. But a question that really remains very open-ended is, how did these stars come to be in the first place? We have evidence that stars evolve and die. And so therefore, and likewise, we now know that stars have not always existed since the beginning of time. Stars also form. So how stars form is the part of astrophysics that really fascinates me. That's what I did my PhD in. That's what I continue to do research in. So for this first part, let's just recap on just the idea of how do you form a star. The interesting but somewhat lengthy answer is that, well, it's through a complex interplay of fluid dynamics, magnetic fields, gravity, turbulence, cosmochemistry, past star formation byproducts, galactic shear, and this all happens after you let it all simmer for about 10 million years or so. That's the complicated answer. That's the interest. And we'll dig into some of these details during this talk. But if you take anything away from this section of the talk of just how do you form a star, I like to say that usually, more often than not, the answer in astrophysics is gravity. How does anything work in astrophysics? Usually it's gravity. The basic idea behind forming a star is that you have a lot of gas kind of swirling out there in the void, and you need to somehow collect all of that gas into a more small, condensed, centralized object, like a star. And if you can get enough of that stuff, that gas becomes hot enough that it can begin glowing, doing nuclear fusion, and creating new starlight. So star formation needs you to collect a bunch of stuff together. That's ultimately the goal. So where is this taking place? We can look at galaxies like ours and other galaxies around the Milky Way. And we find evidence that star formation is occurring primarily in the spiral arms of spiral galaxies. And we know this because we can look at the kind of light that is coming from these spiral arms, and just how different stars are different colors. That is, again, a way of saying that different kinds of stars emit different kinds of light. And it turns out the very, very most massive giant stars emit very particular kinds of light, which we see primarily in the spiral arms. And why that's relevant for star formation is because the most massive stars live incredibly short lives. They have more fuel to burn, but they burn through that fuel at an ever faster and faster rate. So if we can find a place that has very, very big stars, we know those stars could not have existed for very long. So that gives us evidence that since we see all the massive stars in the spiral arms, it is in the spiral arms where star formation is primarily taking place. We can now work that in not only with observations, but we can tie that in with physics. And now our idea of how spiral galaxies operate has improved. And we now know that spiral arms are essentially cosmic traffic jams, where material that is orbiting around the center of the galaxy essentially gets temporarily stuck in these large, grand design spirals. And again, that supports the idea that stars, how do you form a star? You want to form a star in a place where you can collect a bunch of stuff. You want gravity to be able to pull a bunch of stuff together and form it into a hot condensed object. So it makes the most sense that where you can find regions where that can take place is in the spiral arms, where all of this material is essentially being stuck in a grand cosmic traffic jam. Here is one of those regions. My favorite region, one of the few I can find. I always say if you want to stump a professional astrophysicist, ask them to point out something in the sky, because I very rarely have to look at the sky. I'm usually doing all my stuff pen and paper on a computer. But one of the ones I can find is the Orion Nebula. I can find the Orion constellation. I can look to where I imagine his sword might be if he were to sheath a sword. And that fuzzy patch of light I see with the naked eye is not actually a star, but it's actually the Orion Nebula, a 10 or so light year size region of gas that is forming hundreds, possibly thousands of stars as we speak. it appears primarily bright because of 4 very big bright stars in the center, which we call the trapezium, and which is why it makes it very easy to see that the immense amount of starlight coming from those 4 stars makes the entire region glow. But actually, beyond just visible light, we can actually look using different kinds of radiation to see that star-forming regions are actually much more complex than they may appear here when you look at the Orion Nebula, where it just kind of looks like a kind of bright big ball. These large gaseous clouds that eventually collapse to form stars do not glow primarily in visible light like stars do, but they glow primarily in infrared, a different kind of radiation. An IR camera, if you've ever played around with an IR camera, is looking at infrared radiation. So we can look at the same piece of the sky, but look at it using infrared instead of visible, and we get something that looks like this. Again, same part of the sky, but I'm just looking at it in infrared instead of visible light. And you see what we call the Orion Nebula is actually part of what we call the Grand Orion Complex, where is a large, hundreds of light years potentially, region of the sky, where all of these various pockets of gas, like you have some bright stuff going on up here, and where the Orion Nebula is, all of those regions are eventually trying to collapse and condense to form many, many individual stars. So in understanding those regions, what we have to do is we have to try to, through observational photographs, try to piece together a narrative. And while we have gotten amazing photographs from telescopes about what these star-forming regions look like, nonetheless, it remains a very complicated problem and a very big challenge to do. These snapshots, a telescope really, it's just getting a snapshot of a process that really takes place over millions of years. And no NSF grant is going to allow us to wait millions of years so that we can eventually get a movie of what's going on in the region. So observational astronomers have the challenge that they have to look at individual snapshots and try to piece together a longer narrative. And that becomes way more challenging because these regions are complex. For example, they are not just nice quasi-static balls of gas, but they're varied and exhibit complex internal structures. Supersonic turbulence is usually a word that you might hear associated with star formation, that the gas is moving around in these voids of space at speeds that can rival 4, 5, 6 times the speed of sound in space.
Just pat myself.
And so, right, so that just makes it harder to understand. Magnetic fields also pervade these regions. So the magnetic fields, like a common everyday magnet. Magnetic fields play a role in kind of helping to navigate how gas can collapse in on itself. Magnetic fields actually do not like to be compressed. Magnetic fields like to spread out if possible. So if you have these clouds where gravity is trying to bring everything together, the magnetic field can resist that sort of compression and can make it harder for stars to form. The stars themselves can sometimes make this an even harder problem to tackle. Stars themselves, young newborn stars, are very much like young newborn babies, in that we say that they exhibit bipolar outflows. There's constantly material that's being ejected from both ends. These jets introduce a lot of mechanical feedback, or just injects energy and momentum into the region, which helps to stir everything up and actually adds to all that complex motion that you were seeing, I talked about earlier. Furthermore, the fact that there are multiple stars around, usually you don't form just one big star, usually you'll form hundreds of stars, maybe even thousands of stars. And all of those stars are essentially just roaming around, competing for the gas that is trying to either become new stars, or some of the other stars might roam around and kind of steal some of the gas for themselves, because they themselves have a gravitational tug on their surroundings. And of course, we know stars primarily because our sun is a star and that our sun is very bright. So these stars also emit a lot of radiation. That radiation makes it an even more complex problem, because that radiation can heat up the gas. It can push things around when you have very, very bright objects. And so the radiation coming from these stars also adds an added layer of complexity to understanding star formation. So that is where the role of simulations come in. Trying to do this and understand a multi-million-year process can be very challenging when you look at individual photos. However, on a computer, simulating for millions of years is something that's a little bit more doable. It also helps us to get kind of an evolution picture to see kind of how, given a starting point, how you might get to an endpoint. So this simulation, while quite old at this point, remains kind of one of my favorite because it's very illustrative. And that you take a giant ball of gas that has some complex internal motion, and you just turn gravity on. And you let gravity do its thing for about 250,000 years. And what's going on is gravity is trying to pull things together. All the while there's magnetic fields, there's random motions that are trying to kind of spread things apart. And what's happening is that that big ball of gas is not just collapsing to a point, but it's kind of becoming this rich, intricate web of filaments and complex structures. And you see as the movie zooms in, eventually gravity is able to succeed and individual stars start to appear. So all those little white dots you see roaming around are individual stars that have formed. And these individual stars, notice, are not forming kind of just isolated and by themselves, but all of these stars are forming relatively close to one another. And so they're interacting with each other as well as the big cloud that they live in. So it follows that around for a little bit. But connecting all these intricate kinds of physics to a broader picture becomes much more tractable with simulations, because we can essentially look in 4 dimensions. We have 3 dimensions of space, 1 dimension of time, and we can piece together not only what's going on spatially, but temporally as well. And you can see this ending point, it started, remember, as a big ball, and now it's collapsed to this kind of very complex structure that you see. And not only looking globally, but we can use simulations to kind of look at what's going on individually with stars. So here's one particular star that is formed. We're kind of looking at like a bird's eye view of what's going on. So gravity is trying to bring gas together. That's the colors that you see. So that's the gas. The reds and the yellows are more gas versus the blue, which is more tenuous. In this interplay, notice it's forming a big disk. We call that an accretion disk. You notice in this case, something very interesting happens as we let enough time continue on, this big disk around this newborn star pops out, what's that? Another star. And now we have 2 stars that appear to be roaming around each other. And we have seen, in this case, the formation of a binary star system, 2 stars that are orbiting each other, just like how the Earth orbits the sun. But now instead, here it is 2 individual stars. And this arose during the star formation process. So that is nice, because simulation can sometimes reveal how things emerge, right? We were able to see the formation of the binary star system, where with snapshots of the sky, we either see things as it's already happened, or see things as it's currently happening and has not yet progressed to a point where we might be able to see a binary star. And through both simulations and observations, we've actually already come to find that binaries are quite common in star-forming regions. When I look at places like the Orion Nebula, Perseus, Taurus, other clouds that we know are forming stars, we see evidence of either stars orbiting each other, where we might see 2 points of light that are very close to one another, which suggests they might be bound as a binary. And with the next generation telescopes like the ALMA telescope, and hopefully if it ever launches JWST, we will be able to actually peer even deeper into these gas clouds and start to get even more unprecedented detail about what is going on as all of this gas gravitationally collapses into stars. You can see an example here in the lower left. It's an example of kind of zooming in on this kind of pocket of gas. So this just represents a dense pocket of gas. But with things like with new radio telescopes like ALMA, you can see that that dense pocket of gas actually appears like it has 2 individual condensations, which likely means it's going to form into 2 individual stars, which likely will then become a binary star system. So in the star formation phase, it seemed like binaries may be very common. Some have even suggested they're ubiquitous in the star formation phase. So that alone, I would say, is interesting enough to think about, okay, we should learn a little bit more about binary star systems and understand their origins. But they have another role. There was a mention of double stars at the beginning of the session, is that if you look up into the night sky, it is believed that almost 50% of the stars you see are part of some multiple star system, where what might appear like 2 points of light very close to one another, that might actually be 2 stars that orbit around each other, or individual points of light might somehow be connected to other stars you may or may not be able to see, and they all orbit each other through their own mutual gravitational interactions. So the fact that binary stars also appear to be very common in what we would call the field, or just the night sky, suggests that understanding their origins is an important question, since they seem to be very prevalent in what we see. This individual statistic, just to give one last piece of motivation, this individual statistic of how often are binaries a thing also plays a very important role when we try to look beyond the Milky Way and look at other galaxies. When you look at a distant galaxy, you can't see individual stars. We only can really see individual stars in our own Milky Way. When we try to look at distant external galaxies that are not the Milky Way, we don't see individual points of light, but instead we just see kind of a mass, I would say an integral of all the light that we see. You see just the collection of the total light. And people who study galaxies want to know, given this amount of light, how many stars does that represent? And it's important to know how frequently you expect binaries to occur, because that affects your statistics, sometimes by factors of 2, as to how many stars there actually may be in those systems. So knowing that that light is coming from, say, 2 smaller stars compared to 1 big star can play a very important role for kind of galactic evolution astrophysics, where they're trying to think about what is the census of our galaxy and other galaxies. Finally, just at the end of stars' life, so I kind of talked about the beginning of a star's life, kind of the middle of a star's life, just everyday stars in the night sky. Binaries also play a very important role at the end of stars' lives, because knowing the fraction of stars that are in binaries allows us to predict things like how often we will expect something called a type 1a supernova. So a type 1a supernova originates when you have a binary star system where one of the stars becomes a white dwarf and then kind of sucks the mass from the other star onto its surface and eventually explodes as a result. That sort of supernova requires, obviously, a binary system. So if we knew how many binaries were out there, we would be able to make a more accurate prediction as to how many supernova we should be expecting to see. And then whether or not we do, we can then ask more interesting questions. So hopefully that gives you a sense that binary stars play an important role in many, many areas of astrophysics. So for this evening, I want to focus on kind of 3 questions that I have found interesting when thinking about binary stars. What makes a binary a binary? Do binaries yield clues to the star formation process? We see a lot of binaries when stars are taking shape. So the question I like to ask with regards to binary stars is, do binaries appear to give some sort of clue as to what's going on in the star formation process? And then finally, hopefully with time, I want to talk a little bit about what are the next steps. If I can understand the star formation phase, how can I use that information to try to go out to understand the binaries that we see in the night sky? What makes a binary binary? This one is actually very simple. This is my only slide on that question. And why it's very simple is because you all are already familiar with all the physics you need to know to understand what makes a binary binary. This goes all the way back to Isaac Newton's thought experiment of firing a cannonball around the world. Essentially, it's asking what makes an orbit an orbit. So Newton's thought experiment was, if you were to take, say, a ball, and I were to throw it out in front of me, gravity from the Earth would eventually pull the ball to the ground. If I were to then pick up the ball, throw the ball again, but throw it a little bit faster, it would make it a little bit farther, but eventually would reach the ground. Now imagine a scenario where I have nothing in my way, completely open field, and I throw the ball incredibly, incredibly fast. In that case, the ball will be traveling and gravity will still be pulling the ball towards the ground. But by the time the ball eventually makes it to the ground, it might be the case that the Earth itself is starting to curve away because of the Earth being round, the Earth itself is curving away from the ball as it falls to the ground. So in the limit, you can imagine throwing the ball so hard that by the time Earth's gravity brings the ball to the ground itself has curved away. And if you can do this so that the ball never hits the ground. And that was Newton's idea of what makes an orbit an orbit. The way I describe in my intro astro class is that an orbit is a fall and a miss. The moon is constantly falling towards the Earth, but always missing, thankfully. The Earth is constantly falling towards the sun, but always missing, thankfully, because of that additional sideways motion that it has. The same idea with binaries, except now instead of the Earth and the moon, you just replace it with two different stars. They are pulling on each other. They are constantly falling toward each other, but they keep missing each other. That creates a binary star system where they orbit each other. And this sort of physics has been in the news a lot lately. I will not talk about gravitational waves, but you have likely seen a lot of articles about gravitational waves where you might have two black holes or two neutron stars that are orbiting each other. That is a binary system. And in the case of neutron stars and black holes, the environment is extreme enough that they can actually emit gravitational waves and might eventually collide with one another. Eventually they stop missing. Luckily, that effect is essentially non-existent with stars, so I do not have to worry about understanding relativity to understand binary star systems. All right, so for the second question, my question is, do binaries help us understand star formation? And by that, I mean, do binaries allow us some sort of unique probe into the star formation process? If there was something that I could find that is different from, say, Orion to Perseus or Taurus or other star-forming regions that was somehow connected to binaries, that might be giving me clues as to what is going on in the star formation process. Or vice versa, that might give me clues where if I see a certain kind of cloud, I might be able to make accurate predictions as to, say, how many stars are going to form and how many binaries might I ultimately expect. There are things that we have measured in star-forming regions that do not seem to be very sensitive to what's going on. For example, there's this thing we call the initial mass function. So it sounds fancy, but all it really means is the relative distribution of stars. So how many big stars are there compared to medium stars compared to smaller stars? And that seems actually very fascinatingly, very insensitive to the star forming environment. So if you go to somewhere like Orion, which is very dense and very crowded and lots of stars, and then you go to somewhere like Taurus, which is very sparse, not many stars are forming these days, they have very similar distributions of stars. They might have different overall numbers of stars, but the relative amounts, how many bigs versus how many mediums versus how many smalls, appears to be a constant throughout the entire Milky Way, which that's another question in star formation of why it seems to be so invariant. Binarity, however, happens to not, actually does appear to change with different properties. So the plot I'm showing you on the screen it's showing the fraction of binaries, so the fraction of stars that are in binaries as a function of how old the region is and how old the stars tend to be. So the fact that the dots are going towards the lower right, all that is saying is that older regions and older stars are less often in binaries when you look at star-forming clouds. So that's interesting because that means there's something that is changing. And when I look at different regions that might be different ages, I might learn different things based on how many binaries I see, for example. It becomes a little bit more complicated though, because you can also look at different parameters, like, for example, how dense the environment is. So I hinted that the Orion cloud is a very dense environment. There's thousands of stars that are all kind of crammed together versus something like Taurus, which is a very sparse, very old region. All the stars are much more spread apart. And if I look at the fraction, and then Perseus is a third one that's kind of in the middle. And if I look at the characteristics and try to see, and then ask myself, how many binaries are there in each of these regions? There's another trend that doesn't quite perfectly jive with the age thing I just showed before, but is likely related. So there's something that might depend on the age of the stars or the age of the region. It might also depend on the environment itself. Is it a very densely packed region? Is it a more tenuous region? That might make sense because we see that in very dense regions, there are fewer binaries. So you might think, okay, maybe binaries are forming, but maybe there's, it's a very crowded environment. Stars are interacting with each other. Maybe the binaries are getting ripped apart in some way because of gravitational tugs and pulls. That could be one argument. So trying to understand how binarity probes these different characteristics of the clouds. How does it relate to the age of the clouds, the environment of the clouds? Is kind of one of the ways we try to tackle questions like this. How is binarity informing global properties and vice versa? We can also look at the microscopic scale. So the star formation process occurs through the collapse of gas. And we could ask ourselves, is that process, the actual physics involved of how you go from gas to star, is there something that binarity can inform us about with regards to how that occurs? And so there we could ask ourselves, okay, how does the binary actually take shape? How do I get those two stars orbiting around one another? And so here's an example of kind of a distribution of the different kinds of binaries that have been observed in the Perseus cloud. And the axes were very weird numbers, so I blocked them. But really, the taller the bars, that just means more binaries. And the x-axis, or the horizontal axis rather, is telling you about the separations between stars. So how far, if we put a ruler between the two stars as they go around one another, are they close together? Are they far apart? And then how many are we seeing at each of those different separations? And to give you a sense of the numbers here, you might notice, maybe I'll take that away real quick. You might notice that there are kind of two peaks that we observe. There's a peak here where there seems to be lots of binaries here, and then lots of binaries here, and then there's a little trough here. And so to give you a sense of what numbers those correspond to, we're seeing a peak of binaries that have separations that are about the size of the solar system, about 100 or 200 times bigger than the distance between the Earth and the sun. So there seem to be lots of binaries that have stars very close to one another. And then there's another collection of binaries where the separations appear huge, almost 10% of a light year. So that's something like thousands of times just the size of the solar system. And we could ask ourselves, are those two kind of bumps, the small solar system binaries and the very widely separated binaries, are they forming in the exact same way? And if that's the case, why do we then get this kind of weird distribution? Or maybe we're seeing two different formation mechanisms. Perhaps we're seeing binaries can form through two different avenues. And that has been the leading idea. The leading idea is that these peaks we're seeing two different ways that stars form. One is disk fragmentation on the smaller scale. So that's one of the movies we saw earlier where we saw a second star kind of popped out of the disk that was already existing around one of the other stars. So that would be what we call disk fragmentation. Where on the larger scales, that just might be overall turbulent fragmentation, where you have this big cloud, lots of crazy things are happening, and maybe you just get two stars that form relatively close to one another, but close enough so that their gravitational tugs on each other then lock them together, and they become a binary. So that's been the idea as of now. As to how these peaks might arise. So again, the binarity is giving us a clue perhaps as to how the actual stars are forming themselves. However, this model struggles with some other observational data. So here I reproduce the same plot you saw before. This distribution that you're seeing is for all of the stars in this particular cloud. So it has the young stars, it has the older stars, all the stars that have very recently formed, both young and old. You're seeing this kind of distribution of binaries. We could compare that to a similar plot where I only look at the stars that have been around for a while. So I look at the older stars that are in binaries. And we get a distribution that looks a little bit more like this. Where notice the two peaks have gone away. Now it seems like there's only one peak. And that peak seems to be at smaller separations, solar system sizes compared to 10% of a light year size. So something's happening as the stars get older or as time goes on. before we had kind of these two different avenues, but something happened so that all those big separations, all the stars over here, all of those guys somehow go away. And you could ask, are they going away because maybe they're short-lived? Maybe they get, disrupted, gravity pulls them apart or something. Or maybe there's some sort of evolution going on. Maybe something is happening to these objects that make them become something like this. So you could ask yourselves, is this evolution or survival of the fittest in terms of how binaries themselves may evolve? And what is that telling us about the evolution of the cloud? So if you're puzzled how we answer this, you're not alone. It's a very hard question. Fortunately or unfortunately, that gives me kind of many avenues to tackle when I try to explore this very intertwined, complex interplay, rather, between environment, the environment they're forming in, the dynamics of the stars themselves, and just what's going on as a function of time. And then all of this is on top of the fact that we then have to understand how we go from what we see in, say, Orion and star-forming regions to how we then can explain the general night sky. And again, this all is taking place over tens of millions of years. So enter my work of using simulations to understand these questions. The idea here is that I want to study how the environment impacts star formation. So the way you might do this is that you might run simulations that are very, very similar to one another, but are different by one particular factor. And in this case, what we're going to do is we're going to vary the magnetic field strength. So we're going to run I ran three simulations of some cloud that is trying to form stars. One of them had a very weak magnetic field. One of them had a kind of intermediate magnetic field. And one of them had a very, very strong magnetic field. Remember, magnetic fields tend to resist star formation. So the stronger magnetic fields make it harder to form stars. One of them had a very, very strong magnetic field. Remember, magnetic fields tend to resist. Hearing myself as an echo. So someone may be unmuted and want to mute themselves. Very strong magnetic field. Remember, magnetic. Thank you. So the idea here is, and so you might think, why the magnetic field? Well, really, it's the case that this is the beginning of many, many different kinds of projects where we're going to explore many different kinds of things and see how the answer changes. If you're trying to figure out which knob on your stereo changes the volume, you don't twist all the knobs simultaneously. You twist them one at a time and try to find the one that changes it in the way you expect it to change. Here, we're changing one knob at a time, trying to then understand how by changing that knob, it changes the answer. In this case, how many binaries ultimately form and what kinds of binaries form. So the first step is to kind of get these simulations going. You first generate clouds. You first generate a cloud that kind of, I will then just let gravity do its thing and collapse to form stars. So this kind of animation I showed you is kind of just how I just generate these clouds. I essentially just take a big numerical spoon and I stir up the gas and I stir it up in such a way so that they look representative of the sorts of clouds we see in the Milky Way. And then all I do is I turn gravity on and I walk away for 6 months and I come back and my computer hopefully has not crashed and has given me an answer. So this kind of gives you a picture of kind of what that process looks like. So these are kind of very simple movies that show the three different simulations as gravity continues to pull things together and stars begin to form. So these little white dots you see represent individual stars that are forming in these clouds. And I'll replay the movie. So that is just the first part of my journey. And that really what's happening is I'm creating three different data sets. Now I have three clouds where stars have formed. And now I have all of this data, both in position and time. And I can start to ask, okay, of all of these stars that formed, how many are binaries? What kind of binaries are there? And how are they changing with time? Which kind of gets you to the main point of this question. You can already notice some of the trends like what we've talked about earlier. So if the case of a very, very strong magnetic fields don't like to form stars. In this case, only 5 stars ultimately formed. Versus in the very weak magnetic field, 25 stars formed. So I have lots of stars to analyze and look at, But you can see they also seem to be very crowded. There are very crowded environments in this case compared to them being a little bit more spread out for the other cases. So we can now see kind of how that impacts things. Here's an example of just kind of what one of these systems might look like. So this is the same 4 stars, but you're just looking at it from 3 different points of view. And you can see that it's not, again, it's not a very simple picture. It's that you have all these stars, some of them, so there are 2 binaries in this case. They're all kind of orbiting each other and they're kind of being tossed around as they gravitationally pull in one another. And then you have all of this gas that is also being pulled in. So you've got binaries kind of flying around with each other, playing some sort of intricate stellar dance. But on a computer, we can then ask, we actually have a little bit more data and we can actually look at the properties of these binaries and see what's going on. So what do we find? We find that stronger magnetic fields result in more binaries. If we look at the 3 simulations, all this plot really is showing you is that as we look at the 3 simulations, the stronger the magnetic field, the more binaries ultimately are left over and maintained at the end of the simulation. So even though the weak magnetic field case, which is the dark blue case here, it formed 25 stars, but ultimately had fewer and fewer binaries over time compared to the other 2 simulations. Again, likely a result of the fact that all of those stars are in very crowded environments and they're yanking on each other, and those binaries that are trying to form get completely disrupted. So magnetic fields appear to regulate binary formation. It seems that magnetic fields help keep binaries around. We also noticed, was one of the first to actually observe that, in the 70s, someone claimed that binarity might be ubiquitous. Maybe all stars ultimately form in a binary at some point, and then maybe some of those binaries go away. Like our sun does not appear to be part of a binary system. But it has been suggested that maybe it was part of a binary in the past, and then something happened. We actually saw evidence for this hypothesis from the 70s, where we found that over 80% of the stars were part of a binary or a multiple at some point in the simulation. So I defined this in the paper as singles, orphans, and multiples. And really all that's saying is the singles, those are stars that were formed, but never at any point in the simulation were part of a binary. The multiples were ones that are part of a binary, and they were part of a binary at the end of the simulation. Where what I call the orphans those were cases where they were stars that were part of a binary at some point, but something happened and the binary got destroyed and the stars kind of went their separate ways. So if we include the orphans and the multiples in one group, that suggests that during a star's life, we got that almost 85% of the stars in our simulations were part of a binary at some point, which gives some support to the idea that binarity may indeed be ubiquitous, though perhaps not completely forever lived. So you could ask, what could be causing that? What is the origin for these orphans? So the idea behind, or at least our theory as to what's going on here with the orphans, is we noticed that as these binaries were kind of evolving and taking shape and interacting with each other, a thing that we ended up calling membership swapping was occurring. So this is when you have, say, a binary over here and a binary over here, and maybe they come close to one another, and they might kind of exchange stars as the members of the binary. So in the case, there's ultimately, I think, like 3 or 4 stars. There are a couple of binaries, but the actual binaries themselves, they're kind of passing stars back and forth to one another. And in this case, this was actually a very stable scenario where the 2 binaries kind of passed stars between one another, and they just kind of did this little dance where they exchanged stellar members with each other. That's kind of the nice version. The less than nice version is when you have something like this going on. Membership swapping is occurring, but then there might be some beast that comes in, like what you're seeing at the top, that perhaps also wants to play. But it being so big and massive, ultimately ends up disrupting the entire system. And in that case, some stars might be completely thrown apart, or binaries might be completely destroyed in that case. Here's kind of a zoomed out view of what you were seeing there. So you kind of had a collection of two sets of stars. There's some gas that has a kind of disky structure around it. But as you can tell by watching this movie, you know, two binaries kind of come together, only one really wins. In that case, the more massive one, kind of just its gravitational influence ripped and shredded the other binaries apart. And you can kind of see the stars themselves kind of get thrown off in different directions. So that would be a case of an orphan. You know, it was a binary at some point, something clearly happened and got disrupted, which was fun to see. Another question you could ask is about how do binaries evolve? Remember, we had that distribution, that bimodal distribution, where we thought there was disk fragmentation, and then we thought there was turbulent fragmentation. And that's how you get very tight, small binaries, and that's how you get binaries that are very widely separated. And the question was, is there's two different formation mechanisms, or is there some sort of evolution? What's going on? And we actually see evidence for the latter. We see evidence that binaries evolve in terms of how far apart the two stars are. We find that the binary themselves become smaller and smaller with time. So what you're seeing here, you're kind of seeing three stars that are dancing around each other. But kind of the takeaway is that the two stars in the center initially are, you know, you can kind of see, I can see two individual dots. They're very widely separated at first. But as time goes on, notice that the two stars get closer and closer to one another until eventually they're just kind of overlapping each other. So they started with very big separations, but eventually the binary appears to have shrunk so that the two stars are orbiting each other at much smaller separations. So we're seeing evidence of the kind of what we call shrinking binaries. You know, binaries appear to be evolving from the widely separated to the small. And so we can try to make sense of this. Don't worry about the colors. All this is showing you is that larger separations are on the top, smaller separations are on the bottom. And as you go from left to right in each of the panels for the three different simulations, that's showing you what is happening to the separation as a function of time. And this kind of nice one in the middle is kind of very nice and representative. You can see that the binary starts with a very large separation at about 10% of a light year, actually. And then it shrinks down, down, down as time goes on. So eventually that binary has shrunk down to something that is about 100 times the size of the solar system. And to remind you, remember, those were the two scales that we defined this peak here, the small peak, and the widely separated peak. I can even highlight them on this plot. These two vertical lines correspond to these two shaded regions at large separations and small separations. So again, notice if I just kind of squint a little bit, on average, it seems like most binaries are starting very big, widely separated from one another. And then as time goes on, they appear to be shrinking to smaller and smaller separations and maybe appear to be piling up kind of at the 100 times the size of the solar system distances. So that suggests that maybe this is not two different formation mechanisms like has previously been thought. Maybe actually what we're seeing here is we're seeing some sort of temporal evolution. Because remember, all the old stars appear to have very small separations, which makes sense given this model. You give them enough time, their wide separations shrink and shrink and shrink, and you eventually get very small, tight binaries, like what we see in this peak on the left. Now there I could just claim victory, but I would be a bad physicist if I just claimed victory without trying to provide a justification. I need to provide some sort of model, some sort of idea for why this is occurring. The simulation is showing it happening, but I should be able to kind of give a simple idea kind of why it's happening. So the model I proposed was this is an example of something that's called dynamical friction. So the idea behind dynamical friction is that you have a big object, a star, which is drawn in blue in the center, and it's moving to the left. While it's moving to the left, it is gravitationally pulling in all the local gas. It's trying to pull gas onto itself. That's how the star gets bigger. So it's trying to suck in and gobble up all the mass that's around it via gravity while it's moving around in space. Now the idea behind dynamical friction is while the gas is falling onto the star sometimes moves too quickly and moves out of the way. So as it moves over to the left, all the gas falls in, but misses the star and actually instead falls behind the star. So it creates, it creates ultimately a dense wake kind of behind the star. So you have a lot of extra gas behind the star compared to what's happening in front of the star. And that large wake of gas tugs back gravitationally on the star as it's moving. And that actually acts to slow the star down, which is why we call it a friction force. So that is dynamical friction of gas that is trying to fall into the star, but misses. So we modeled this. We took two examples from our simulations. Those are the black curves you're seeing in the plots. So that's the separation between the stars as time goes on. And I came up with a very simple model that incorporated dynamical friction as a way to explain these separations. And that is what's being shown in red. And obviously a model is great if it really does represent the data. So again, I can't see anyone. So I assume you are all standing and applauding at this point because the red curve and the black curves overlay one another pretty good, pretty well. This was a very good day at work down in Texas. Because it's always nice when you can come up with an explanation that is fairly simple. I don't need tons and tons of bells and whistles to understand what's going on. I can simply just think of it as, okay, gravity is pulling a bunch of gas in, but some of it is falling behind the star by accident, which is kind of tugging back on the star. And as a result, that makes the star, instead of just going around in circles, you can think of them as kind of spiraling in toward each other. Obviously, we don't want this, we can't have this go on forever, else they will collide, which it seems to very rarely occur, essentially never, at least by what we saw. But that's great. You know, it's a very simplified idea of kind of how we can explain what is going on in these things. So, and again, that kind of gives an idea to, is it actually disk fragmentation and turbulent fragmentation? Are they two different things? Maybe instead what we're seeing is some sort of evolution. Maybe it's all turbulent fragmentation with maybe a little disk fragmentation. But maybe why we're seeing that distribution is more evolution compared to different kinds of formation mechanisms. All right, I have about 5 more minutes, which I think puts me in a perfect spot. So I will come back to this slide, but that is just kind of a summary of kind of what we've been looking at right now. It's like, so this work, which took place over the last couple of years, and really explored in depth for the first time, the formation and evolution of binaries on a computer. And the idea moving forward is that I'm now doing these same simulations again, but now I'm twisting a different knob. Instead of magnetic field, maybe this time I allow the stars to have their bipolar, outflows, and to see how including different kinds of physics, how that changes the answer and allows us to start to think about how it, whether or not it accurately reproduces what we see actually out there in space. And if it does, can we then come up with models and ideas of how what we're seeing by these snapshots that observers are taking came to be. But I have not answered, there are 2 questions that still remain unanswered here. That's kind of the immediate and the now, kind of what I'm working on. We still have to somehow connect this to the field. We still have to come up with a way that describes the night sky. For example, I form way too many binaries in my computer compared to what we see in the sky. I'm saying 80% of the stars might be in binaries, though we only think that 50% are actually binaries when I look at the night sky. These individual snapshots of star formation also, right? Usually most of the stars have not formed yet when we look at, say, Orion or Taurus or something like that. Many more stars are on their way, but the gas is still collapsing to form the stars. So since observers can't wait around millions of years for this to happen, one could also ask, is there something that might give clue to what's going to happen in terms of what sorts of binaries might be forming, whether it's going to be a binary at all, that maybe we can look at the gas itself to try to get a sense of what's going on. So let me take a couple minutes to kind of propose some ideas behind these 2 questions. And I like these because I get to accent the work of undergrads that have been doing this work with me. Let me take the first one. Connecting to the night sky. the double stars you see and love to look at through telescopes. Connecting to the field is challenging because just looking at the sky itself, observers really have a very challenging time in doing what they do. The fact that they are able to do anything, with confidence just shows how good they are at their job. Because an observer, when you look at the night sky, or what we sometimes call the celestial sphere, the entire night sky appears like a 2D dome that is surrounding the Earth. You don't see into and out of the sky. You only see everything as if it's plastered on some big sphere that's surrounding the Earth. So the way that binaries are typically identified for observers is they look for stars that appear to be very close to one another. Like in the case of here, Albireo, those two stars appear to be very close to one another and appear to be about the same distance from one another based on other measurements. So it's suggested that maybe the Albireo double star system is actually a binary, where the two stars are orbiting each other, compared to, say, just a visual binary where they appear close but might not actually be related at all. And of course, the other famous one that's fun to look at is Alcor and Miser in the Big Dipper. But that one's even more interesting, speaking of binaries, because as I'm sure many of you know, Alcor and Miser themselves are multiple star systems. What we call Miser is actually a set of 4 stars, 2 binaries orbiting each other. And I believe Alcor is itself a binary. So there are 6 stars total in what we call Miser and Alcor. And there, again, the question is, are these actually true binaries? Or do they just appear close to one another in the sky? So in undergrad, Angela Karam here at St. Mary's has been considering this question of just given a 3D distribution of stars, how often do we expect an observer who is only seeing a projection or a 2D projection of that 3D space, how often do we expect that they might be making a mistake? Here is kind of a movie he made that I think really illustrates this well. So what he does is he takes my simulation data, which has stars in 3 dimensions, 3D space. And he essentially just takes it and looks at it from a certain point of view and sees and imagines as if he's an observer and plasters my simulation data against the sky. So here in this movie, you might think, okay, there seems to be a cluster of stars up here in the upper right. That looks like they might be close to one another. And just look at the red stars for right now. Where over here in the lower right, it also seems like, okay, those two appear kind of close to one another. Maybe that's a binary as well. But this is just one point of view. So Angela rotates the image for us. And you can see how the 3D distribution of stars can sometimes mislead you based on how you're viewing the stars. In the case of the stars that were in the lower, used to be in the lower right, now is in the lower left after this rotation, notice the 2 stars, which are the ones in red, the actual locations of those stars appear widely separated in that 3rd dimension. So it is very unlikely those 2 stars are actually gravitationally bound to one another, even though at the very beginning of the movie, it appeared as if they were very close to one another. My screen appears to have frozen, so 1 second. Angela's movie apparently was too much. It might be that this is where we end it. Yes, I seem to have lost control of my screen, unfortunately. All right, well, in that case, then I can just kind of convey what was going to be next while I try to figure out what is going on with my screen. In this case, what he does is he essentially does this process, but he repeats it bunches of times. He looks at my simulation data from multiple points of view and tries to determine, given thousands of different approaches to looking through the simulation data, how often if I treated them like an observer would, how often are mistakes being made? And it turns out, actually, that it seems that around 50% of the time, there's at least one mistake that is being made by observers. How you identify stars in a star-forming region might actually, in this case, the mistakes might be more common than we previously thought they would be. So that is interesting and an open question. And I wish I had a plot to show you, but again, my screen seems to have given up on me. But I can still hear you, so presumably you can still hear me. Right, so I could just kind of summarize with what have we learned through this exercise? Kind of my takeaways here are that magnetic fields appear to regulate star formation. It seems that magnetic fields help keep binaries around for longer amounts of time. And that allows binaries to persist and perhaps exist out into the everyday space. My work has suggested that binarity may indeed be ubiquitous. It might be the case that all stars do eventually are part of a binary at some point in their lives. But how long, but it must be the case that not all of those binaries appear to be long-lived. And that may occur because of dynamical evolution that's going on with the stars. The stars themselves are interacting with each other in the gas, and it may be that binaries are evolving from big separations to small that then eventually may get completely destroyed. And then the final point to be made here is that how we connect that to the sky itself. You know, this summer working with Angelo actually turned out to be, this question turned out to be more fascinating than I had even originally believed, even though I thought it was pretty fascinating to start. The idea that it might be the case, and more work has to be done, that the binaries we think we see in the night sky, that it may be the fact that more mistakes are being made than previously thought. So how we can help observers do a better job is the kind of another future step we're taking with these simulations. How can we help observers do better with this? That they're already very hard task.
Tab here.
All right, thank you so much for listening. I will end it there, and I'm happy to take some questions, assuming you can all still hear me.
Oh, well, I'm gone because I didn't hear enough of it.
So again, my screen has frozen, so I do not know if you can still hear me or not.
Yeah, we can hear you.
Okay, yes, then if I cut out, that is essentially the conclusion of my talk, but unfortunately the slides are no longer advancing for me.
Nobody's got a question. Thank you.
Yeah, so I can take some questions if there are questions, but someone will have to play moderator, unfortunately.
This is Mike Rinaldi.
Hi, Mike.
Hi. Back where you're doing dynamical friction, is that something that is analogous or similar to what's going on in the spiral arms?
So the spiral arms, probably not. So the spiral arms, what we think is the idea behind spiral arms is that the spiral arms themselves are not, actual objects themselves. They're actually just kind of locations in the galaxy where things come in and out of. But as you move through the spiral arm, you're not slowing down really as you move through the spiral arm, but the spiral arm is kind of moving with you as you move. So you kind of get stuck with a lot of other stars and stuff for some prolonged period of time.
It's like a standing wave or something like that.
Indeed, yes. Yes, since I can use words like that, since you just did, yes, exactly.
Okay. All right, thank you.
Right, if you wanted to look up more, it's the spiral density wave theory, I think is what it's called.
Okay, thank you.
Yeah.
I do have one more question.
Sure.
This is going back to the very beginning where you showed the black, the LIGO black hole kind of merging. What I guess is it a combination of mass and proximity that would cause it to produce gravitational waves, which would cause it to lose energy and spiral in, or and is that the reason why normal binaries don't do that, or do normal binaries do that anyway, but at a much slower rate, much slower rate, I should say.
Right. By the theory of general relativity, yes, anything that's kind of spinning around each other is doing something like this. But the effect really only manifests itself in any sort of meaningful way when you have things like neutron stars, black holes, which can have masses like the entire sun. You know, a neutron star is essentially if you take the entire mass of the sun and cram it into a ball the size of San Francisco.
Right.
So in that case, you have incredibly intense gravitational pulls as a result. So if you have two of those guys pulling on each other, the thing, you know, the environment is extreme enough that you do get kind of ripples in space, which are gravitational waves. That sort of thing does still occur with things like stars, but you know, those are, you know, and again, like the merging black holes or the merging neutron stars, those objects are separated by miles, you know, compared to, you know, 10% of a light year, you know, like what I'm talking about here.
Right. Okay.
So it is, I think you said this exactly. It's a combination of kind of like intense mass limits as well as proximity, that you just have two very compact objects very, very close to one another.
Okay. Right. Thank you.
Yeah. Yes, and the fact that we've been able to detect gravitational waves, you know, that has also been like a huge, exciting development. Essentially, a new branch of astrophysics has been created in the last couple of years with things like LIGO being able to detect these very, very faint ripples in space-time. Yeah, so if you have not, I would recommend, yes, you should find something to talk about gravitational waves. Yes, my computer just is not giving in.
Liz, are you there? I'm not hearing it. Can anybody hear this is Linda Mahan. Can anybody hear me?
Yeah.
Yeah.
Liz, I can hear you, Linda.
Yes, we can.
Okay. I just wondered if you were able to put people's questions forward that had typed them out on their computer.
So I could ask someone if you want to try this, if you don't mind. One of the people who are a host, one of the people that are the host, you can force my screen sharing to stop. And I'm wondering if that will help me kind of break free of this trap I'm in. And then I might be able to actually see you as I answer your questions. But yes, if people have written out questions, yes, if someone could read them out loud, that would be great.
Thomas, are you able to stop the screen sharing on Aaron's screen?
Let's see, let me try something. So I'm still here, but I have essentially shut off my computer and
There
joined.
you go.
Oh, there you are. Oops. No, you were there.
Yeah, so now I'm here and I can actually see all your lovely faces. But you're right, the slide should go away eventually once it realizes my computer has been turned off.
Aaron, this is Mike Rinaldi again. I have one more question.
Of course.
Could you elaborate a little bit on how magnetic fields cause star formation to, or I guess binary formation? I guess they increase binary formation? The greater the
So they
field.
help retain binaries. The idea is that, given a binary, if it exists in an environment with a stronger magnetic field, as a result, it seems to be able to persist, versus in the more crowded, chaotic environments when there is a very weak magnetic field, then you tend to get, chaotic disruption events that occur.
Okay.
All right, so there are kind of two things going on there, right? There's the idea that they help keep binaries around, but they also, as a result, produce fewer stars. Magnetic fields alone make it hard to form stars, just in general, because they're a combatant against gravity. Gravity is ultimately just trying to pull everything together. Magnetic fields does not like to be compressed, so they try to push everything apart.
I see. Yeah. Okay, that's the one that. Okay, that makes sense. Thank you.
Yep, of course.
Did we have any other questions? Did anyone type in a question, but Aaron wasn't able to see it on his screen? Would you like to read that question out loud at this time?
I do not see any, but it's possible that since I rejoined.
No, I don't see any coming up here either, Aaron.
Okay.
But if you think you're speaking and asking a question, you might be on mute. So double check that in case you have a question that you want Aaron to answer while we still have him.
Of course. Yes, I think that is the slogan of 2020. I think you're on mute.
Yeah. Seems we may be out of questions then.
All righty.
Linda?
Thank you so very much, Aaron, for speaking to us tonight. I'm glad this is recorded so it can be reviewed a second time, third time. And it will be very interesting to have you back sometime in the future.
I would love that.
Yeah, good.
Thank you again for having me.
And of course, I'm
Next
hoping we
time,
can
exactly.
be in the auditorium and hear you and see you and take you to dinner before your talk.
One question.
Sure. That was Jim that was speaking, I think.
Mm-hmm.
Yeah. So the work with your graduate student.
Undergrad.
Does that, undergrad, exactly, yeah. Does that indicate that there are less binaries than we thought, as it appears to suggest? And then how would that impact the theories that you're dealing with?
Right. So the idea here is that, with what I'm doing, the benefit of me doing it on a computer is that I have way more information than observers have. So I'm not convinced it impacts what I'm talking about in my simulations, but it does make the transition of how we connect what I'm doing to whether or not it agrees or disagrees with what we see in the sky. It makes that a more complex and interesting question. Because, if, say, the statement that we think 50% of the stars in the night sky are binaries, a question now might be, well, is it really 50%? Or, worst case scenario, 50% of those are wrong, so maybe it's only 25%. So more work needs to be done thinking about this, but some of the preliminary results raise some eyebrows and are pretty interesting.
Aaron, I have a question.
Yeah.
Over the years, we've looked at double stars, and a question that people ask when they're looking at them is, are they connected gravitationally or are they line of sight? And there's usually some place that I can ask that question and the answer is given. Is that question based on the kind of observations you're doing now, or is that speculation as to whether they are in fact gravitationally bound or just line of sight?
Yeah, so in some cases, right, so the way, right, just because, so an example I think that is not debated is say like Miser and Alcor, where we can see kind of roughly where they are in the sky. They appear close to one another. We have a good sense based on the light they emit, kind of how much mass is around. So we know kind of how much they might be able to influence one another's motions. So by kind of combining multiple pieces of evidence, we can fairly confidently say, yes, this is definitely a binary. And in some cases, and those, you know, they are too widely separated for us to actually see them moving. Obviously, if we see them going around each other, that obviously is great evidence. But in the cases where we just see still images, right, usually you're picking apart and teasing together different kinds of observations to try to make this picture true. So the other one I showed, Albireo, actually, you know, I feel like once a decade or so, it seems like there's reestablished debate on whether Albireo, or what we at Berkeley called the Cal star.
Yes, I tell people that too.
The blue gold star, whether or not they're actually bound to each other or not. Sometimes we think, you know, we've gone back and forth as in like, oh yeah, they're definitely bound to one another, and like, oh, maybe they're not.
Mm-hmm. Well, if something was published, say 20 years ago, 15 years ago, is it less firm information than it would be if it were reviewed more recently?
Potentially, right. Potentially it's possible. The field stars, yeah, if they are close to us, because so we have other ways of determining properties of stars. You know, we can sometimes tease out how close things are in the third dimension, for example. Like you might have heard of the parallax method is one way that we can determine distances of stars. Essentially, you oscillate your eyes back and forth, and you see your finger kind of wobble around, and the amount of wobble that occurs is a function of how close your finger is to your eyes. Of course, astronomers don't go out into the sky and start winking their eyes back and forth. We have telescopes that can do this. And so we have a good sense, and the Gaia telescope is a good example of something that's collecting, you know, accurate positions to millions of stars in the local region of our Milky Way, which is kind of a successor of the Hipparchus satellite, which was able to do this for like 10,000 stars or so. So with that additional piece of information, that actually helps a lot, because if we see them close in the sky, but then we also know that they are close to each other in the third dimension as well through, say, parallax, that gives us much more confidence in our answers. That's the long answer. So the short answer is that if the stars are relatively close, you know, within a couple thousand light years from us here on Earth, then we probably are pretty confident in whether or not they're bound or not bound. And the farther away you get, the more murky it might become. That's a good question. I mean, that is essentially at the heart of what we're trying to think about, of just like what really, what sorts of mistakes really should we be expecting here?
Thank you.
Yeah. And I think we do have something in the chat, I see. Yes, just more a comment than a question of that we always question, right? Scientists are always asking questions. That is kind of what we are trained to do. We take nothing for granted. Yes.
I guess that's the end of our questions then.
All righty. Great set of questions. And I apologize again that my screen just gave up on us. Yeah.
There were a couple of technical difficulties this evening. Don't worry about it.
Yeah.
Right.
I'm sure we'll go back and
part of the theme
watch
of
this
this
again
evening.
too.
Yeah.
I'm just going to remind anyone who is listening that next month we will have the speaker begin his lecture at 7:30.
And we'll be communicating that through the newsletter and through the
Right.
SFAA weekly and so forth. So
Right. It's something we haven't usually done, but he contacted SFAA, but then realized, oh my goodness, it's 3 hours later. So that's what he wants to do.
I thought astronomers were night people, but okay.
SFAA had looked through his portable telescope on Mount Tam many times when he was a member. And
We'll get the word out on that. Aaron, thank you very much.
thank you.
Thank you. It's a pleasure again to speak again with SFAA. I really
Yes.
remember fondly
Well, good.
interacting with you way back in the day.
Yeah.
And I look forward to many other times of us interacting.
Thank you so much.
All right. Stay safe and healthy, everyone, and have
You too.
great
Thank you.
Very much.
Thanks.
Bye-bye.
you. Hi, Linda. Ah, elle est partie. Elle n'est pas restée.
Alors, dis-moi comment tu
I don't know.
fais.
Don't ask me. I told you. Don't ask me comment j'ai fait. C'est pas tu m'as
La
dit.
prochaine fois, tu peux le faire aussi.
I have no idea, Jean-Pierre. Je vais essayer. That's all I can say.
Et la dernière fois, je l'ai fait moi-même,
I
ça
know,
allait.
I
Et là,
know.
je sais pas pourquoi.
Mhm. Mais ils ont dit qu'ils ont eu des difficultés
Ah.
cette fois-ci. alors
Ok, bon,
peut-être.
alors peut-être que c'est ça.
Yeah.
Ok, bon, ben ça va. Ok, d'accord, d'accord.
Mais on peut regarder le commencement aussi. Hein.